Hello and welcome to this revision recording by the Further Maths Support Programme. This particular recording is about numerical methods and we're looking at approximations to functions. The specification states two things very clearly in it. The fact that you've got to use Newton's forward difference interpolation polynomial, and that's slightly misleading because you also need to be able to use Lagrange's as well. So the second statement that we have is basically telling you that you use Lagrange's in other situations. So be able to construct the interpolating polynomial of a degree n given a set of n plus 1 data points. So in other words, to do a cubic you'd need 4 data points, for a quadratic you'd need 3, and so on. We talk about x, y values there. So you need to be able to use both of those. Only one of them is written in an easy to recognise form on the formula sheet. Newton's one is on the formula sheet, and so you can refer to it when you need it. Okay, so the first question we're going to do is from January 2010, and it's question 5. And what we've got is a table here of basically, you could think of them as x and y values, and we've got to show by means of a difference table that a cubic polynomial fits them closely but not exactly. And then we've got to use the forward difference formula to estimate the value when x is 1.5. So the good thing here is we can use Newton's forward difference formula because the x values all increase by an equal step, which in this case is 1. So the first thing we need to do is to construct our difference table. And so we know that it's going to be approximately cubic, so we actually know how far we're going to go. Normally you just keep adding on the differences, the delta f and the delta f squared f and the delta cubed f, the first, the second and the third difference. You keep adding on until you get to something that's constant normally, but they've told us it's cubic, so I know I need to go to the third difference. So we fill in the x values. So we have 0 to 4, and the gap between them is 1, so I've written down h equals 1 because h in Newton's formula refers to the increments in x. So we fill in the y values. And at this point I reach for a calculator and recalculate the first difference. So I calculate 2.342 minus 1.883. Always the lower value in the table, take away the one above it. When I say lower, I don't mean the size of the number, I mean that it's actually physically written underneath it. So I do 2.342 minus 1.883. Next time I'm going to do 2.874 minus 2.342, which comes to 0.532. So all the time I'm doing the one that's in the lower position, subtracting the one above it. If it was negative, I'd just write a negative in front of it. Okay, so there's the first difference. Then we go through it again and do the second difference. And we get these values. And then we do the third difference. And at this point, we've got something that's a similar value. Now, if it really was a cubic polynomial, then at this point we'd have the same value turning up. It would be a constant. But now we've got to say that that third difference is nearly a constant. And so if that's the case, a cubic polynomial will be quite a good approximation. So it will fit the data closely. We need that statement in there as well. It's not enough just to write in the table and assume that the examiner is going to realise that you've got two things pretty close at the end, so that's fine. You actually have to say it. So that's part 1. We've shown by the means of the difference table that a cubic polynomial will fit the data closely. Let's go back to the question. So now for part 2 we have to show the value of f1.5 using Newton's forward difference formula. And so I need the formula, which is off the formula sheet. Now notice that doesn't go up to the third difference. I have to imagine what the third term would look like. It's going to be x minus x0, x minus x1, and then x minus x2 over 3 factorial h cubed. And then we're going to have the third difference after that. So there's my table, and I'm going to use the values from that. You need to know a few things about the values here. You need to know that that's x0, that's x1, and we're going to need x2 for the term that isn't written in the formula, the standard formula up there, that we're going to have to add to get it to be a cubic. Fx0 is that. Delta Fx0 is the first of the first differences. Delta 2 Fx0 is the first of the second differences, and you'd assume that when we get to delta 3 Fx0 we're going to be using that value. Okay, that's the value that we're going to use for the third difference. It's always that top diagonal line, unless they're asking you to pick out something that fits lower data points rather than the whole lot. Okay, so for this thing it's pretty straightforward. We know the values that we're going to use. We know h is 1, which means h squared and h cubed are all 1. Makes life easy. Then we've only got to make sure that we put in 2 factorial and 3 factorial correctly. So, putting in the values, we end up with Fx0 is 1.883. Delta Fx0 is the first of the first differences, which is where the 0.459 comes from. Delta 2 x0 is the 0.073, the first of the second differences, and delta 3 fx0 is 0.012, the first of the third differences. So that's the first, if you like, y value, that's the first difference, that's the first second difference, and that's the first third difference. This value is x minus x0, so 1.5 minus 0. That's the same, and then that's x minus x1, so 1.5 minus 1. Okay, those two turn up again, and then x minus x2, and that's 1.5 minus 2, so negative 0.5. Okay, at the bottom we have h, there's h squared, there's h cubed, and then we have, if you like, 1 factorial, 2 factorial, 3 factorial. The factorial is increasing. So we number crunch that, we put it into a calculator and we write out what we get, which in this case is 2.598125, and we leave it at that. Okay, now let's see how that would be marked. Here's the full answer, and for your table you would be getting 3 marks. You'd be getting a method mark for using the table correctly. You'd be getting an answer mark for working out the first difference correctly. You would get 1 answer mark for working out the second and third differences correctly, with a follow through. So if you've mucked up your first difference, that wouldn't necessarily mean you'd lose the marks for doing the second and third. But notice it's got not many marks on it for quite a lot of work, so you have to be very, very careful and accurate. The final thing is, you needed that explanation there. It wasn't good enough just to leave it as a table. You had to say that it's because the third difference is nearly constant, you can fit a cubic polynomial closely to it. So that's 1 mark for the explanation on that. For actually working it out, you got 1 mark for knowing to use the polynomial in the first place. And then you get an answer mark for, I would say, every pair of terms that you have there. So every pair of correct calculation terms that you've got in there, you get 1 mark. And finally, 1 mark for getting the answer correct. Okay, so the next question is May 2010, question 5 again. They're not always question 5. This is all in one go, and this is using the other one. So we've done Newton's forward difference formula, and the first thing this actually says is explain why you can't use it for this particular case. And then it asks you to use Lagrange's interpolation formula, and so we're going to use the other one. And it's best on Lagrange's if you learn what to do, as opposed to trying to use the formula from the formula sheet. It uses a lot of nested notation in that, and it's not always that easy to read. So the first bit, you have to have an equal increase in x values. So in this case, you can't use Newton's forward difference formula because the x values don't go up by the same amount each time. They go up by 2, then 3. so they don't increase by equal increments. Now, for Lagrange's interpolation formula, we can start off by writing fx equals, and I'm going to show you where the values come from on this page, and then we'll simplify it on the next. It wants us to get it in the form ax squared plus bx plus c. So, what you do for Lagrange's, and it's always best if you learn what to do. For 3 points, we get a quadratic. It's always one order less than the number of points that you have. You start off with the first y value, which is negative 10. And you multiply that by x minus, and then you use the x values that are from the other 2 points. So we just used a y value from the first point, which was negative 10, and then we use the x values from the other 2 points. So we use the 3 minus 12 and the 630, we use the 3 and the 6 from those. And that will be at the top of the fraction. At the bottom of the fraction, we use the same x values we've just used, the 3 and the 6, and we're going to subtract them. But we subtract them from the actual x value, which is 1. So from our first point, the x value is 1, so we get 1 minus 3 and 1 minus 6. And so we should get that nice pairing up. And we make sure we have that each time. There will be the same to be done for each of the other 2 y values, the negative 12 and the 30. But what I always do is I always write it as a plus and then keep it as a fraction. So I've now got plus, and then I'm now on the negative 12, and I do x minus the x values that go with the other points. So x minus 1, x minus 6. And I'm going to put that over 3 minus 1 and 3 minus 6. So that's my second fraction. And then my third fraction is 30, and x minus 1, x minus 3, and then 6 minus 1, 6 minus 3. So that's Lagrange's. It's always fairly straightforward. Just learn how to do it rather than trying to use that formula. Learn how to do it. So it's quite straightforward. It's the y value, and then x minus the other x values as sets of brackets over the actual x value minus the same values again, as many times as you have y coordinates. Now the next bit, of course, is to simplify it. And in each case, a fair amount could be done. We had negative 10, and that actually divides by the number that we have at the bottom. So if you calculate the numbers at the bottom, it all comes out. So we end up with negative 1, and then I've multiplied out the quadratics, but I kept them in a bracket so that I don't make any algebraic mistakes and sign mistakes. And so the next stages are really about simplifying it. And at the end of this one, the value that they've got plus c, well, the c is 0, so you could write plus 0, but it's good enough to write 3x squared minus 13x. Okay, let's see how that's marked. So there's 7 marks for it. So you get an explanation mark for saying the first thing. Then, for using the polynomial correctly, you get 1 mark for attempting to do it, so you get a method mark, but you get 1 answer mark for each of your 3 fractions. You get an answer mark for the simplification stage, and you get an answer mark for the final answer. So that's how the 7 marks are split on that. Next paper, January 2011, another question 5. So this time, looking at the table, it goes up 1, 3, 5, 7, 9, it goes up in 2s. It's probably going to be a Newton one, and part 1 asks us to use a difference table to determine the least possible degree of polynomial. Now part 2 says, assuming that it is of that degree, extend your table to find the values of when x is negative 1, what y is, and when x is 11, what y is. So I'd make sure you read the question first, because the best thing here is just to leave the space in the table for part 2. So my table. Now this time I don't know where to finish, so I'm going to fill in some things I know I need, which is the x values, if you like, the y values, the function values, and then the first difference. Now notice I've left a big gap, that's my minus 1. I've left a big gap at the end for 11. And because I know that this is to do with Newton, I know that h is 2. So I fill in the y values and then work out the first difference. So 3 take away negative 10. You always do the value that's lower in the table, take away the one that's above it. So 3 take away negative 10 is 13. 44 take 3 is 41. 129 take 44 is 85. And 274 take 129 is 145. Now it's not linear, it's not of degree 1 because those aren't a constant. So I'm going to need another heading. And so I calculate 41 take 13, 85 take 41, and 145 take 85, and I'm beginning to get worried because it looks like it's going on forever. So let's try the third difference. I get 16 and, phew, 16. Right, that's enough to tell me that a cubic polynomial will be good enough there. The third difference is a constant, so I need that statement. I can't just leave it, and I need to say this time that it is constant, so a cubic polynomial will fit all of those data points. Okay, I now need to work out negative 1 and 11, so I'm going to work backwards. So I know that I'm going to need to work out these values, so I now need to think, well, what values would make that work? 28 takes 16 is 12. Okay, and then for the other end, 76 takes 16 is 60. So now I've got 13 take 12 at the top, and if I add at the bottom, I get 221, and then I can fill in that, and that means it goes with negative 1 and 11. So what I've done is I've worked my way back through the table. And so I'd summarise that by writing down that P negative 1 is negative 11 and P11 is 495. Okay, so let's look at the marking for that. The first time through. Okay, the first set of marking up here. That's the first time through. And for our difference table, we get one method mark and one answer mark. For the third difference being constant as a statement, we get an exclamation mark. The fact that we then conclude that it's cubic gives us a follow-on mark, not a follow-on mark, but another mark for that. Okay. Then for the next stage, for working out negative 1 and 11, we work forwards. Now, what they mean by working forwards is that on this one, we're adding to go that way, so that works us forwards to 11, and working backwards, which is this, each time we're subtracting there. Okay, there we go, to get that for negative 1, so that's working backwards. So we get 1 for the method, which if you think is basically adding or subtracting, and then 1 for the answer, which is the negative 11 and the 495. Okay, now on that last one I did write down h equals 2 because it looked like Newton's polynomial one. In fact, we never needed to use it. Okay, so this one's a different question. It's a question 3. So last question I'm going to look at is from May 2011, question 3 of the last straightforward question. So we've got a quadratic function. It's known to be quadratic. We've got to write down the value of Q0 obtained by linear interpolation. Now, this is not going to be that onerous to write it down by linear interpolation. It's not really just use your common sense, okay, on it. I'll show you how I did that. Then it's asking us to use Lagrange's method to write down an expression for it, and then find the exact value of Q0 from Lagrange's method. So we'll get the exact polynomial from Lagrange, and we'll be able to find out Q0. So here's our values. From negative 1 to 1 to 0 we want to find is between those two. So obviously linear interpolation uses 2 points either side of the thing we want. So we want when x is 0. So we have negative 4 and negative 12. And what's exactly halfway between them? Because 0 is halfway between negative 1 and 1. So in this case it's a really simple idea. You just have negative 8 there because that's halfway between negative 4 and 12. Okay, for part 2, using the correct formula. Okay, we're not going to use the 0, negative 8. We're going to use the other values that we had in the original table. So the first y value was negative 4, And the x values that don't go with that are 1 and 5. So I've got x minus 1, x minus 5. The x value that did go with the negative 4 was negative 1. So underneath it I've got negative 1 take 1 and negative 1 take 5. Next y value was negative 12. And we have x plus 1. That's just x minus minus 1. Okay, so that's x plus 1, x minus 5. And then the x value that went with the negative 12 was 1. So I've got 1 take minus 1. So 1 plus 1. 1 take 5. Then the final y value is 20. There's the x values going in, and it's 5 take negative 1 and 5 take 1 underneath it. It didn't ask us, by the way, to simplify that. That's what they mean, just leave it as it is. It then wants us to work out the exact value of Q0, so we substitute 0 into our whole expression that we had before, and then we number crunch it. We just type it into a calculator. I put a little bit more effort in than that. I worked out each individual term, just in case they got it marked like that, and it comes out to negative 10. So the marking. Writing down the value, you see it does actually say you could just write it down. 1 mark. So writing down negative 8 is 1 mark. Then for part 2, for getting it in the correct form, 1 mark. For having 3 terms, 1 mark. And then for each of the terms, 1 mark. Okay, so there's a lot of marks for that compared with the previous time we've had to do that. Then calculating the value when x is 0. Notice that I did put far too much effort into that. 1 mark for the method, 1 mark for the answer. Now this really is the final question, but it's much longer. So I've done the last of the section A questions, and this is what happens if you get a section B question. So we've got a section B question that's going to ask us to use Newton's forward and difference interpolation formula. The x values go up by 2. And it wants us to find a quadratic that fits the data. Notice again it says there's no need to simplify your answer, so 6 marks without having to simplify it. Then we've got to estimate what F2 is and F6 and state which one's most likely to be more accurate. And then it gives us another value and asks us to find a cubic, 7 marks, and then we've got to estimate F2 and F6. And then we've got to comment on the changes by going from having a quadratic estimate to a cubic estimate. So I'm going to run through this fairly quickly. The difference table is what we need for our Newton's interpolating polynomial. So we need the x values, the y values, and we need to go as far as the second difference. Okay, so there it is all calculated. Negative 2 take 4 is negative 6, 10 take negative 2 is 12, 12 take negative 6 is 18. H is the gap between the x values, which is 2. So there's our interpolating polynomial. First y value is 4. The x minus x naught is x minus 1. The negative 6 is the first difference, and then we've got to divide that by h. So negative 6 divided by 2. Okay, the next term, the second difference is 18, and then we have x minus x naught and x minus x1, so we have x minus 1 and x minus 3. Then we have h squared, which is 4, times 2 factorial. And it doesn't want that simplified. So that's it. Okay, 6 marks for doing that. Then we've got to estimate the values of F2 and F6. So we have to stick in 2 into that, and we number crunch it out. We then stick in 6 into it, and again we number crunch it out. So we just worked out our polynomial, we just stick in 2 and then stick in 6. We get those values. We then had to say which one's more accurate. Well, the way we worked out the polynomial is we used values between 1 and 5. So 2 is between those. It's an interpolation. Whereas 6 is outside of that. It's an extrapolation. And extrapolation tends to, on the whole, be less accurate than interpolation. So the interpolated result is going to be more accurate. So we have to have that as our reason. Okay, so part 3. We now have to find a cubic that fits it, given that we now know when x is 7, y is 11. or fx is 11. And then we've got to estimate f2 and f6 again. So if I increase the table, I get a negative 29 for the third difference. And I'll be doing that on the table that I've already created. So the interesting thing here is that the first three terms are identical, it's only the last term that's any different. And we should realise that before we start. So really the difference is going to be in that last term. So again we have the third difference, which is negative 29. Then we have x minus x0, x minus x1, x minus x2, so x minus 1, x minus 3, x minus 5. And then we have h cubed, which is 8, times 3 factorial. We calculate again what f2 is. Now notice here I've not bothered to calculate it with x equals 2 in the whole of what I've written above. I knew that the first three terms came to negative 1.25, and in fact it's only that extra bit, that the negative 29 thing, that I have to calculate. So I've now got a new f2 just by adding on, if you like, a corrected value, that last term. Do the same with f6. Okay, so we've done parts 1, 2 and 3. Now part 4, it's only 2 marks, but I couldn't see a quick way of seeing this without doing a little bit of legwork. So we've got to comment on the absolute changes and the relative changes in the estimates of f2 to f6 from going from part 2 to part 3. So it's important we know which way we're going from part 2 to part 3. So I've written down the two values of f2 and the absolute change, because we're going from part 2 to part 3, it's with the change from negative 1.25 to negative 3.0625. So I do second value take first. So the absolute change is negative 3.0625 take away negative 1.25, which is where we get negative 1.8125 from. The relative change is found by dividing that by the value that we started with, which is the one from part 2, the negative 1.25. So I've divided by negative 1.25, so I've got the absolute change and the relative change. I then do the same with the f6 values. So the absolute change is it's dropped by 9.0625, so it's negative 9.0625. The relative change, if I divide that by 22.75, the value I started at, I get negative 0.39835. And then, looking at the absolute changes, which was A, it's bigger for f6. And that's what they really want. It's only 2 marks, so there's 1 mark for doing that. And then looking at the relative change, it's bigger for f2. And that's really all they're going to want from those 2 marks. So let's look at the marking of it. For the original table, 1 mark for the method, 1 mark for the answer. For the original function, 1 mark for the method, and then 1 mark for obviously each step in the answer, so for the 4, the negative 6 and so on for each fraction. Then for part 2 you get 1 mark for working out f2, 1 mark for working out f6 and 1 mark for the explanation. There's the improved table with the extra value. For x equals 7 we get 1 mark for the method, 1 mark for the answer. And you'd get that if you'd added those values onto your original table. There's not a problem with that. Okay, then we get 1 mark and 1 method mark and 1 answer mark for the new function. That's really because all we're doing is adding on that extra term. So the answer mark is for the extra term. For calculating the new values are 2 and 6, you get 1 mark for the method and 1 mark for each answer. So you'd only get 1 mark for the method because it's a repeated method for each one of those, and 1 mark for the answer. And then there's 1 mark for each of your explanations. Now I still can't see, there's no method mark for all the extra work I did, but I couldn't have seen it by just a quick glance. So I suppose I could have thought about the numbers, but it's much better to be sure. So I've actually done the 2 calculations in each case, and so I've got that comparison that I can make, and 1 mark for each explanation. Okay, and that's the end of this revision session from the Further Maths Support Programme.